Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where your thoughts can unwind and wonder is allowed to move gently. Tonight, you and I will wander into a landscape of mysteries, a place where the universe speaks in soft riddles and distant signals. But before you settle in, if you find comfort in these sleepy explorations, feel free to tap the like button or subscribe, only if it feels right in this quiet moment. And when you're ready, you can share in the comments where in the world you're listening from and what time of night it is for you now. It's always a joy to see how many little lights across Earth gather here at the same time, each in its own slice of darkness. So if you haven't already, you might dim the lights, let your shoulders relax a little, or let a soft fan hum in the background. And when you're comfortable, we'll begin our slow drift into what the universe has been trying to tell us, sometimes in clear voices, sometimes in whispers, and sometimes in puzzles so strange they seem almost like dreams. The universe has always been a storyteller, though not in the way humans tell stories. It speaks through light, through patterns, through the quiet arrangement of galaxies that span billions of years. Some of its messages are straightforward, shaped by familiar laws and gentle rhythms. Others feel like accidental poetry, brief flashes, sudden dimmings, rings hanging in space, or empty regions that stretch far beyond what our models say they should. And every once in a while, the universe leaves something that simply does not fit. Something that sits quietly at the edge of our understanding and asks us to look again. Tonight's journey is about those strange pieces, moments when astronomers pointed their instruments at the sky and found something so unexpected, so stubbornly unexplained, that even after decades of trying, the questions are still larger than the answers. These are not the loud mysteries, the ones shouted into science fiction headlines. These gentler, subtler, sometimes fleeting events that appear once and vanish forever. A 72-second signal that arrived from somewhere near the constellation of Sagittarius and never came back. A star whose light fades in patterns so irregular and deep that it almost looks as though something is moving across it. A traveller drifting through our solar system from another star, shaped in ways that make no easy sense. Vast cosmic rings and arcs so large they stretch across billions of years of distance, arranged in ways our theories did not predict. And quiet voids, immense hollows in the cosmic web, where almost nothing lives, though by all calculations something should. Each of these discoveries is like finding a page in a book, written in a language we only partly understand. We can recognize the letters, we can sense there is meaning. But the full message still sits just out of reach, and rather than closing the book in frustration, scientists have learned over centuries to lean in closer, to let curiosity rather than certainty guide the way. Anomalies are not threats, they are signposts pointing toward new territory. If you think back to the history of science, nearly every major leap forward began with something that didn't fit. A tiny deviation in Mercury's orbit eventually opened the door to the theory of relativity. Peculiar bright points in radio maps turned out to be the first hints of supermassive black holes. A faint, steady glow in the sky revealed the afterglow of the newborn universe. In each case, the strange thing came first. The explanation followed later. Mystery, then understanding. Confusion, then clarity. Like a tide that moves slowly but never stops. In the same way, the mysteries we will explore tonight may look isolated at first. A ring of radio light here, a silent signal there, a void stretching across a corner of the sky. But if we listen closely, gently, without rushing toward conclusions, a pattern might begin to emerge. Not in the sense that all these phenomena come from the same cause, but in the sense that they all point quietly, consistently, toward the idea that our picture of the universe is still incomplete. And that is not frightening. It is beautiful. It means there is more to learn, more to uncover, more to wonder about than we ever imagined. As we begin, try to let your thoughts drift lightly, like dust motes settling in still air. There's no need to grasp every detail. The universe has never demanded perfect understanding, only curiosity. We'll move slowly, one discovery at a time, like lanterns illuminating a path through a dark field. Each lantern will cast a gentle glow on something strange, a signal, a star, a structure, a silence, and together they will paint a picture of a universe that is far more flexible, more surprising, and more imaginative than our current equations suggest. So breathe in softly, let the night around you deepen, and allow yourself to step quietly into a world where the unexplained isn't something to fear, it's simply an invitation to keep listening. The journey begins with a single moment, a single signal, a brief whisper that once rose above the cosmic background. A whisper that said nothing we could decode, yet refused to be ignored. A whisper from a direction we still revisit, hoping one day to hear it again. And from that whisper, our exploration unfolds. There is a quiet kind of suspense that settles in when you look for something without knowing what form it will take. That was the feeling decades ago when a pair of giant radio ears, simple, white-painted metal structures in Ohio, were listening to the sky with patient attention. These instruments were not designed to see light the way human eyes do. Instead, they listened to the sky the way you might listen to a distant coastline at night, hoping to catch the faintest hint of a voice carried by the wind. And on one warm August evening in 1977, the sky answered back. The telescope was called Big Ear, a name that suited it perfectly. It didn't move the way modern dishes do. It simply sat still, allowing the spinning Earth to bring different parts of the sky across its listening field. For the most part, the telescope heard only the usual cosmic murmur, the soft background hiss of the universe, a smooth, familiar sound. But then, for just over a minute, something remarkable happened. The hum suddenly spiked upward, growing stronger and clearer like a single note rising sharply above the background of a sleeping city. That brief rise in signal lasted about 72 seconds. It came from near the constellation of Sagittarius, in a region of sky that astronomers often watch because it lies in the direction of our galaxy's crowded centre. The signal's pitch sat near what scientists call the hydrogen line, but instead of using that technical term, imagine it more simply, a quiet, natural radio tone that atoms of hydrogen tend to hum at. Hydrogen is the most common element in the universe, and its natural note is a favourite place to listen, just in case any other beings out there might decide to speak using a wavelength nature already whispers in. The strength of the signal rose smoothly and fell smoothly, exactly as you would expect from something fixed in space as the Earth rotated under it. It wasn't jagged or messy. It wasn't scattered across many frequencies. It was focused, about 30 times stronger than the common cosmic background. And then it faded out gracefully. Nothing about it felt accidental. When the data was printed out the next day, a long sheet of numbers showing the strength of the radio noise at each moment, one researcher circled the spike and wrote a single word in the margin. Wow! It wasn't a scientific description. It wasn't a formal classification. It was simply a human reaction, the kind that escapes before you can think of a more careful phrase. And from that moment, the wow signal earned its name. Trying to understand what the signal was is a little like trying to recall a conversation you only overheard once, far away, in a crowded place. You have no recording, you have no context. You only know that for a short moment something sounded unusual, and then it disappeared. Some scientists proposed that maybe a comet swung through the telescope's view at just the right moment, reflecting or producing a faint burst of radio energy. Others wondered if it could have been a natural cosmic object, something we simply haven't catalogued yet. A few asked whether the signal could have come from our own planet, bouncing oddly off something in orbit. But one by one, those ideas began to fall away. Comets were checked, and none lined up convincingly. Terrestrial interference usually leaves fingerprints, uneven noise, strange patterns that the WOW signal did not have. And as for unknown cosmic sources, nothing we have observed since behaves in quite the same way. It was too clean, too narrow, too focused, almost as if someone or something had chosen that exact pitch on purpose. It's important to speak of that possibility gently. Science is not built on excitement alone. It moves slowly, cautiously, leaning first on what is most likely rather than what is most dramatic. But the truth is that the most likely explanations have not held up well, and the most dramatic one, an artificial signal, has not been ruled out either. What remains is a puzzle, a whisper with no second whisper to compare it against. Astronomers went back many times, pointing more sensitive instruments at the same patch of sky. If the signal had been a regular broadcast, we would have heard it again. If it had been a natural cosmic flare, it might have repeated at least once. But the sky offered only silence, night after night, year after year. The WOW signal remains a single solitary moment in time. There is something strangely comforting in that. Not because it suggests an answer, but because it reminds us that the universe still holds secrets that refuse to conform to our expectations. Even with all our telescopes, satellites, and data processing tools, far more than the scientists of 1977 could have imagined, we cannot explain everything we see. Sometimes the sky gives us a melody, and then hides the instrument that played it. If you imagine the universe as an enormous, dimly lit room, then the WOW signal was like seeing a match flare once in a far corner, brief, bright, and gone before you can turn your head. It might have been nothing more than an accidental spark. Or it might have been a sign that something else is present in the darkness, something that leaves traces only when chance allows our paths to cross. Today, when researchers speak of the WOW signal, they do so with a mixture of affection and frustration. It is one of the cleanest, clearest, unexplained radio events ever recorded. It contains just enough strangeness to make us wonder, and just enough uncertainty to keep us from drawing conclusions. In that way, it mirrors the earliest moments of scientific discovery, the ones where curiosity sits quietly beside humility, and neither tries to outshine the other. And perhaps that is the lesson of the WOW signal. Not that we are being contacted, not that we are alone or not alone, but that the universe is wider, older, and more surprising than we expect. Sometimes the sky speaks only once. Sometimes that is enough. If the WOW signal was a whisper, a single fleeting note in the dark, then Tabby's star is more like a lamp whose glow keeps fading in ways no one can predict. Not switching on and off like a faulty bulb, not pulsing like a heartbeat, but dimming in uneven, irregular motions, sometimes gently, sometimes dramatically, as though something large and shifting were drifting across its face. And every time astronomers think they have understood one pattern, the star seems to offer a new one, erasing earlier assumptions with a kind of quiet mischief. This unusual star sits about 1,460 light-years away from us, far enough that the light reaching Earth now began its journey in the early days of ancient civilizations. To our telescopes, the star appears slightly larger and hotter than the Sun, with a steady, bright rhythm. At least, that is how it should behave. Most stars of its type shine with dependable consistency, varying only by small amounts over long stretches of time. But Tabby's star refused to follow that script. The first hints of its strange behaviour came from a space telescope that watched thousands of stars continuously, looking for tiny dips in brightness caused by planets passing in front of their host stars. These dips are usually small, sometimes only 1% or less, like a speck drifting across a flashlight beam. But Tabby's star did something that startled even the scientist accustomed to odd data. Its light sometimes faded by 15%, sometimes more than 20%. And these episodes didn't follow a pattern the way a planet's orbit would. They appeared suddenly, lingered unpredictably, then dissolved into normal brightness before returning again weeks or months later. To get a sense of how strange that is, imagine someone turning the dimmer switch on a lamp, not all the way down but far enough that you would definitely notice, and doing it not once but repeatedly, without any rhythm. And imagine that the lamp is a star, a blazing sphere of plasma so large that even a giant planet crossing in front of it would dim it by only about 1%. A 20% drop is not the shadow of a planet, it is the shadow of something immense. The first explanation people reached for was dust, and that idea makes sense on a basic level. Dust can block light in complex ways, especially if it is uneven, clumpy, or stirred by collisions in a planetary system. But the more scientists studied the star, the more complicated the dust story became. Dust behaves differently depending on its size. Tiny grains scatter blue light more strongly, the way distant fog looks bluish in the evening. Larger grains block all colours more evenly, making the dimming look more neutral. When astronomers measured the dips at different colours, they noticed that the star dimmed more in the blue than in the red, which does suggest fine dust, but there was too much irregularity, too much variation, and not enough evidence of the underlying reservoir that should create these clouds. It was like seeing footprints on the beach without finding the waves or wind that could have made them. Other natural explanations came and went. Some thought there might have been a catastrophic collision in the system, a pair of planets or large icy bodies shattering into a cloud of debris. This could create uneven dimming as the fragments drift across the star, like ashes drifting past a fire. But that should also produce infrared glow as the debris warms, and the infrared measurements never showed such warmth. Others proposed swarms of comets, but comets would again create heat signatures that we don't see. The pattern didn't match their behaviour. Because the natural explanations were struggling, a more speculative idea slipped into the conversation, not as a conclusion, but as a gentle question. What if an advanced civilization had built orbiting structures around the star? Not a solid shell, that belongs to science fiction, but a vast, loose assembly of collectors, reflectors, or panels to harness starlight. The idea is often referred to as a megastructure, though that word tends to ignite imaginations far more than the evidence warrants. Scientists didn't propose it as the most likely explanation. They proposed it as a placeholder, a reminder that when familiar explanations fail, we must widen our thinking just enough to consider the full range of possibilities, even the unlikely ones. Still, the megastructure idea brought a renewed wave of interest. If such a structure existed, it might cast uneven shadows that change as pieces drift or move. The irregular dimming would make sense, but as tempting as the images, later observations found nothing that looked like radio signals, heat leakage, or any of the other signs we might expect from technological activity at that scale. The star was puzzling, but not chatty. Its dimming did not carry messages, it simply changed in its own quiet way. As more data arrived from both ground-based and space-based telescopes, the dust explanation regained strength. Not ordinary dust, but dust that drifts in delicate, unpredictable streams. Dust born from crumbling bodies, evaporating fragments, or perhaps from a cloud of material orbiting at just the right distance. But even that right distance is a guess. The dips still vary. The long-term brightness of the star seems to be slowly declining. The patterns resist a single neat explanation. The beauty of Tabby's star is that it reminds us how little we understand about the worlds around other stars. Our solar system feels like home base, the pattern against which we compare everything else. But there is no rule saying other systems must behave the same way. In fact, the more exoplanets we discover, the more we realise that our system is something of a quiet exception. There are planets that skim their stars in just a few hours, planets puffier than cotton candy, planets that orbit backward. If planets can break our expectations so easily, perhaps the subtle dance of dust around a star can as well. In the years since its discovery, Tabby's star has become a kind of cosmic character. Scientists speak of it fondly, as if it were a stubborn friend who keeps giving half answers to simple questions. Every new set of observations helps a little, yet somehow opens a new question in return. And that is part of its charm. It doesn't shout, it doesn't explode, it simply dims, quietly and unpredictably, as though it were a lighthouse whose rotating beam has slipped out of rhythm. And maybe that is the best way to approach it. Not as a problem that demands quick answers, but as a lantern flickering in the cosmic distance, hinting at processes we haven't fully named. A reminder that stars, for all their steady glow, have complicated lives. That dust is not always orderly, that brightness is not always stable, and that sometimes, when we aim our instruments at the sky, the universe replies not with clarity but with gentle, persistent ambiguity. There are stars that burn steadily, following the familiar scripts that physics has written for them. They shine with predictable colours, reveal predictable elements, and behave in ways that make sense even from hundreds of light years away. And then, every so often, astronomers encounter a star that seems to have skipped rehearsal entirely, a star that sings in a key no one taught it, with notes that should not exist long enough to be heard. Przybylski's star is one of those rare, quiet rebels. To understand why this star is so strange, it helps to think about how scientists study the chemistry of distant suns. When we look at a star through a telescope, we aren't just seeing light, we're seeing a detailed pattern in that light, something like the barcode on a product in a store. Each element, whether it's hydrogen, helium, iron or oxygen, leaves a thin, precise mark on the star's glow. These marks are a bit like musical tones. Every element plays its own note, and the combination of notes tells us what the star is made of. When astronomers first studied Przybylski's star, the notes they heard were confusing. The usual elements were there, of course, but mixed in with them were unfamiliar lines, notes belonging to radioactive elements that should not exist in a mature star. Among them were technetium and promethium, elements that decay so quickly on cosmic timescales that seeing them in a star's atmosphere is like finding snowflakes on a sunlit sidewalk. Unexpected, delicate, and gone too fast to leave a trace. The lifespan of some of these elements is measured not in millions of years, not even in thousands, but in hours or days. A star that has been shining for hundreds of millions of years should not be able to hold them at all. And yet, they were there. Clear, sharp, persistent. Imagine looking at an old tree and discovering fresh green shoots at its highest branches. Not because it is spring, but because something inside the tree is quietly renewing itself. That is the feeling Przybylski's star gives, the sense that it is sustaining ingredients far younger than the star itself, ingredients that should vanish almost as soon as they appear. One of the earliest ideas was that the star might be pulling up material from its deeper layers, dredging up atoms that had been forged in more extreme conditions. But stars are not oceans. Their layers do not mix freely, and the radioactive elements found in Przybylski's star decay too quickly for this kind of stirring to explain them. Even if the star could dredge them up, they would fade away long before we could observe them. Another possibility was that the star had a hidden companion, a smaller partner whose own outbursts or unique chemistry might influence what we see. But careful observations never revealed signs of such a companion. No orbiting star, no quiet neutron star nearby, no fragment of exotic matter lurking in the shadows. Przybylski's star remains alone. As more detailed measurements accumulated, the puzzle grew even stranger. Additional elements appeared, rare Earth elements like holmium and europium, usually found in places where intense nuclear reactions occur. Their presence hints at processes that should not be active in a star of this type. It is as if someone had emptied a small chest of unusual gemstones into a bowl of ordinary stones. The overall mix still looks like a star, but the individual pieces glint in surprising colours. One of the more imaginative ideas suggested that the star might be harbouring what physicists poetically call islands of stability. In simple terms, these would be extremely heavy, exotic versions of atoms, so heavy that they teeter on the edge of falling apart. They would not last long on cosmic timescales, but if they exist at all, they might crumble slowly enough to produce the shorter-lived elements we see today. It's a delicate hypothesis, the kind that walks between known physics and the edges of what might be possible, and yet it fits the mood of Przybylski's star. Quiet, improbable, stubborn. Another line of thought considered whether the star might have been enriched by a passing supernova long ago. The explosion of a dying star scatters exotic elements into space, like sparks flying from a great fire. If Przybylski's star drifted through such a cloud, perhaps it picked up some of these rare ingredients. But even that explanation falters, because the elements would decay long before they could settle into the star's visible surface. What makes this mystery especially gentle and especially frustrating is that nothing about the star is dramatic. It's not exploding, it's not devouring a companion, it's not casting off violent jets or pulsing in strange rhythms. It simply shines steadily, while its light carries a quiet signature of something that should not be there. Many cosmic mysteries announce themselves with noise or movement. Przybylski's star does it with silence. In this way, the star feels like a cosmic riddle written in fine handwriting. Not bold, not loud, but persistent. It asks a question without telling us how to approach the answer. And part of the challenge is that the star lives so far from us that all we can gather is its light. We cannot visit. We cannot sample. We can only interpret the faint colours it sends, hoping that with time the puzzle pieces will settle into place. The story of Przybylski's star is less about one unusual celestial object, and more about the edges of our understanding. Stars have long been our laboratories in the sky. Their light has shown us the rules of nuclear fusion, the life cycles of matter, the composition of worlds we cannot reach. And yet here is a star that seems to say, softly but insistently, that there are chapters in that story still unwritten. If the wow signal was a whisper of possibility, and Tabby's star a dance of shadows, then Przybylski's star is a quiet contradiction. It asks us to slow down, to reconsider what we think stars can and cannot do. And sometimes, those contradictions are the most valuable clues we have. They remind us that the universe is not obligated to behave in simple ways. It behaves in real ways, ways that we must work patiently to understand. And perhaps, somewhere in its shimmering spectrum, Przybylski's star is telling us that the periodic table we know so well is not the final map, that some corners of nature remain hidden, that the universe, even in the light of a single star, still holds secrets we haven't learned to pronounce. There are puzzles in astronomy that shout for attention. Brilliant explosions, rapid flashes, sudden dimmings. And then there are puzzles that whisper. Puzzles that sit quietly, glowing softly, almost as if they expect no one to notice them at all. The Methuselah star is one of those gentle riddles. It does nothing dramatic, nothing chaotic. It simply shines in an unassuming corner of the sky, carrying with it a soft contradiction that has lingered for decades. According to some measurements, it seems to be older than the universe itself. Of course, nothing can truly be older than the universe. Time began with the universe, like the first note of a song beginning with the singer's breath. But the age of this particular star has stretched the edges of our calculations again and again, pushing us to rethink not just the star, but the methods we use to understand cosmic history. To appreciate the puzzle, imagine meeting someone who claims to be older than every tree, mountain, and river around them, older than the world itself. You wouldn't assume they were telling the literal truth. You would instead check the way you measured their age. Perhaps the clock was off. Perhaps the calendar was misread. Perhaps something in their life made them look older than they are. That is exactly how astronomers approach the Methuselah star, also known by its catalogue number, which we can soften as HD 140283. This star is what astronomers call metal poor, though here metals simply means any element heavier than hydrogen or helium. In the earliest days after the universe was born, almost everything was just hydrogen and helium. Heavier elements were created later, inside the hearts of stars or in the violence of supernovae. So a star with very few heavy elements carries a kind of cosmic accent, an old-sounding voice suggesting it was born long before metals became common. When astronomers listen to that voice through its light, they hear a star that formed almost at the dawn of time. One method of estimating a star's age relies on its temperature, brightness, and chemical makeup. These clues tell us how quickly the star has burned through its fuel, much like judging how long a candle has been lit by watching how much wax has melted. The Methuselah star's candle seems to have melted more than expected, suggesting an age of around 14 billion years, and yet the universe itself, according to the best measurements of cosmic expansion, is about 13.8 billion years old. On paper, that puts the star just a little older than everything, an impossible result. But rather than declaring a paradox, scientists began to unwind the problem gently, looking for the small, subtle sources of error that could nudge the calculation back into harmony. The most important of these was distance. If you misjudge how far away a star is, you misjudge how bright it truly is, and from that, you misjudge its age. To refine that distance, astronomers turned to a spacecraft built for exquisite precision, Gaia. Instead of relying on rough estimates, Gaia measures the position of stars with a level of accuracy that borders on unbelievable, like detecting the wobble of a coin on the moon from Earth. By tracking the tiny shift in the star's position as Earth orbits the Sun, Gaia can calculate how far away the star truly is using a method called parallax. But rather than using the technical term, think of it like closing one eye and then the other. Nearer objects seem to jump back and forth more than distant ones. Gaia does this with starlight itself. When Gaia measured the Methuselah star, its improved distance estimate pulled the star's age downward, but not enough to eliminate the tension entirely. In fact, the more precisely we measured it, the more narrowly the age hovered near the upper limit of possibility. It was no longer older than the universe, but it was still uncomfortably close to the line, like a story told with such extraordinary detail that you begin to wonder whether it has been exaggerated or whether something important is missing. Other layers of complexity appear when we consider how stars burn their fuel. If the star contains slightly more or slightly less helium than expected, or if its interior swirls in a way not accounted for in standard models, its rate of aging could shift. Even tiny differences matter. A small adjustment in how heat flows within the star could shave hundreds of millions of years off its estimated age. But those adjustments require changes in our models of stellar physics, changes that reach far beyond this one star. Then there is the possibility that the star formed from an unusual mixture of material early in cosmic history, perhaps enriched by rare processes that shaped its appearance. Or perhaps it was born in a region where early stars lived fast and died young, sprinkling the surroundings with elements that subtly alter the chemistry of the next generation. These ideas are delicate and speculative, the kind that add colour to the story without rewriting its ending. What makes the Methuselah star particularly soothing as a cosmic mystery is that it stays still while the theories move around it. Unlike many other anomalies, explosions, dimmings, or bursts, this star is simply itself. It does not flicker strangely or pulse in unpredictable rhythms. It doesn't swallow companions or cast off violent outbursts. It is quiet, patient, a silent witness to nearly the entire history of the cosmos. And perhaps that is why its story feels almost philosophical. It reminds us that the universe is not a set of exact numbers chiseled into stone. It is a tapestry woven from both light and uncertainty. Every measurement we make is softened by the limits of our tools, our models, and our assumptions. When a star seems to stretch beyond the age of the universe, it is not the universe that is wrong. It is our methods that need refinement, and that is the essence of scientific humility. There is comfort in knowing that even a star can teach us patience. The Methuselah star whispers that the universe is not hurried. It does not reveal its secrets all at once. Some answers take decades, others take centuries, and some, like this one, linger at the edge of our understanding, inviting us to approach gently, ready to revise our thinking whenever new light arrives. As we watch this quietly aging star, glowing softly from across space, we are reminded that time itself is not a rigid wall. It is more like a river whose depth we measure with imperfect tools, and every once in a while a star stands in that river as a stone, steady, ancient, hinting that the flow is more complex than we realized. There is a particular kind of quiet that settles over astronomers when something truly unexpected enters the solar system. Most objects that pass near the sun belong here. They were born from the same swirling cloud of dust and gas that formed Earth, Mars, Jupiter, and all their siblings. Their paths are familiar, their behaviours predictable, their compositions known. But every so often, the sky reveals something different, something that moves as though it has come from impossibly far away. In late 2017, that something arrived. It was small, faint, and fast. So fast that by the time we realised it was here, it was already on its way out. The object was given a name that rolls gently on the tongue, Oumuamua. In Hawaiian, the word suggests a scout or messenger, something that reaches us first from far beyond. It is a name chosen with great care, because this visitor was indeed the first confirmed object to drift into our solar system from a distant star. Most comets and asteroids follow looping paths that eventually return them to the Sun. Their orbits are gentle ellipse, stretched circles that stay bound to our star's gravity. But Oumuamua did not have that kind of path. Its orbit was stretched so wide that it never closed. Imagine throwing a stone past a hilltop. If you throw softly, it rolls back toward you. If you throw hard enough, it crests the hill and keeps going forever. Oumuamua did not roll back. Its trajectory was a long, open curve, a clear sign it had been travelling among the stars before crossing our sky. Even before we learned its shape, Its speed alone told a story. It was moving too fast to have been captured by the sun. Nothing in our solar system could have nudged it into such a path. It was unmistakably a traveller from elsewhere. When telescopes first focused on it, the object looked faint, almost shy. But as it rotated, its brightness flickered in a way that revealed its unusual shape. Not spherical, not potato-like like most asteroids, but elongated. At first, astronomers imagined something shaped like a thin cylinder, perhaps 10 times longer than it was wide. A cosmic shard, tumbling end over end, catching the sun's light in uneven flashes. Later, analyses softened that picture, suggesting instead a flattened pancake-like form. Either way, it was far stranger than anything we'd catalogued. That shape alone would have made Oumuamua special. But then came the second surprise. As it passed near the sun and began to travel outward again, its speed increased slightly. Just a gentle nudge, but unmistakable. It was drifting faster than gravity alone could account for, as if pushed by a faint breeze no one could see. For comets, this is normal. When a comet warms near the sun, trapped gases inside can evaporate, creating jets that act like miniature thrusters. But comets reveal this process with a glowing tail of dust and vapour. Oumuamua showed no such tail, no visible gas, no shimmer of dust. The expected signs were absent. So how do you explain an invisible push? Some scientists proposed that the object released water as tiny, undetectable molecules, too fine to form a visible tail, but still powerful enough to accelerate it. Others suggested that Oumuamua's surface might have contained trapped hydrogen or nitrogen ice, releasing itself quietly as the sun warmed it. These ideas painted the object as an unusually fragile shard, perhaps the broken remains of a distant ice world sculpted by time. Another idea, offered gently and without sensationalism, was solar radiation pressure. In simple terms, this means the faint push of sunlight itself, photons acting like soft fingers. For sunlight to push an object noticeably, the object must be extremely thin, something like a sheet or a flake rather than a solid chunk. If Oumuamua was shaped like a light, delicate leaf, about as thick as paper but many tens of meters long, sunlight could have nudged it exactly the way the data suggested. This idea raised eyebrows not because it pointed to anything artificial, but because nature rarely makes such thin, wide objects. Yet nature is creative. It produces ice feathers on comets, hollow shells in dying stars, and delicate webs in stellar nurseries. A thin shard drifting in from a shattered world is unusual, but not impossible. Still, the shape and the non-gravitational push led some researchers to wonder, quietly, cautiously, whether Oumuamua might be something crafted rather than born. Not a ship nor anything dramatic, but perhaps debris from an ancient, far-drifting structure. A fragment of something that once served a purpose we cannot guess. But this was only a hypothesis among many, and most astronomers lean instead toward a natural explanation, even if it must be an unfamiliar one. The difficulty is that Oumuamua gave us very little time. It passed our sun, glided past Earth's orbit, and slipped away toward the outer dark before the scientific community could bring its full array of instruments to bear. What we know comes from a brief span of days, snapshots, flickers, hints. It is like glimpsing a figure walking across a fog-draped field at dusk, clear enough to know someone is there, too fleeting to know who they are. Some mysteries come with noise. Oumuamua came with silence, and in that silence lies its charm. It reminds us that the universe is full of debris from ancient collisions, drifting fragments from distant systems, cosmic travellers shaped by forces and histories we will never witness. It reminds us that our solar system is not isolated but part of a greater sea, visited now and then by objects that carry whispers of other shores. Its arrival also prepared us for what may come next. Now that we know how to look, we expect more interstellar visitors, perhaps dozens per decade, once new survey telescopes begin scanning the sky. Oumuamua may be the first chapter in a new story, one where we begin to study not just our own solar cousins, but materials from faraway suns and broken worlds. And although we may never know the exact shape or origin of this first visitor, it left behind a simple, elegant truth. The universe is more connected than we once believed. High above us, in the silent dark, objects wander for millions of years between stars, carrying memories of their birthplaces in their shapes and motions. Ever so often, one drifts close enough for us to see, and even if its message is only a faint curve in its path, a gentle acceleration, or a flicker in brightness, we listen. Because listening to these fragile hints is how curiosity grows and how our understanding slowly expands across the night. Most stars live long, quiet lives. They burn for millions or billions of years, shining steadily like lanterns in a dark valley. And when their time finally ends, they do so with a kind of cosmic dignity. Some collapse softly into dense remnants, others explode in spectacular supernovae, whose bright light fades over weeks or months. These patterns have been studied long enough that astronomers can almost anticipate how a dying star should behave. But in the summer of 2018, the sky raised its hand politely and said, "Not always." The signal of this new event came from a galaxy about 200 million light-years away. Far, but not impossibly far. A telescope in Hawaii detected a sudden flare of light that was too bright, too fast and too blue to be anything familiar. Its official name, AT2018 Cow, sounds almost playful, as if the universe were making a small joke. But the phenomenon behind the name was anything but ordinary. This flare did not brighten slowly like a supernova. It rose to its peak brightness in just a couple of days, like a match striking in the dark, and it wasn't merely bright by the standards of stellar explosions, it was tens of times brighter than common supernovae. Then, just as quickly as it rose, it began to decline. The whole event unfolded on a timescale that felt rushed, condensed, as though the universe had pressed fast forward instead of letting things play out in their usual rhythm. Imagine watching a firework, except instead of blooming and fading across a minute, it erupts and vanishes before you've even fully registered it. That is the feeling AT2018 Cow gave astronomers. It was too swift, too luminous, too strange. As soon as the light curve, the gentle rise and fall of brightness, was recorded, scientists started comparing it to everything in their catalogues. It did not match classical supernovae. It did not match gamma-ray bursts. It did not match tidal disruption events caused by black holes shredding stars. It was as though the universe had briefly invented a new kind of explosion. One of the most striking qualities of the event was its colour. It was unusually blue, meaning it was extremely hot. The temperature of the explosion appeared to be higher than ordinary stellar blasts, as if the material was being heated by something incredibly compact and energetic. When astronomers studied how the spectrum changed over time, they noticed that the event cooled far more slowly than expected. Ordinary explosions expand and cool quickly. This one seemed to stay warm, its energy refusing to disperse. Something inside was pumping out power long after the initial flash. This led to the first hypothesis. Perhaps AT2018 Cow marked the birth of a black hole or a neutron star. When a massive star collapses, its core can squeeze into something unimaginably dense. A neutron star packed as tightly as the nucleus of an atom. or a black hole whose gravity is so strong that even light cannot escape. The problem is that these objects normally hide behind the debris of the explosion, but in AT2018 Cow, the debris seemed thin or perhaps blown outward rapidly, leaving the newborn object more exposed. It was as if the veil usually drawn across these final moments had been pulled aside, letting us glimpse a formation process that had only been theorized. Another idea suggested that the event might not have been a dying star at all. Instead, it could have been a smaller, compact star, something like a white dwarf, being torn apart by a black hole. In most tidal disruption events, the shredded material forms a luminous disk that emits ultraviolet and X-ray light. But in this case, the process would have to happen faster and more violently. The pace of the brightness changes suggested something unusually small and dense was involved. A black hole only a few times the mass of the Sun could, in theory, rip apart a white dwarf with terrifying efficiency, leaving behind a flash of light that rises and fades almost before we have time to name it. Yet another possibility involved collisions between compact remnants, perhaps a white dwarf smashing into a neutron star, or two neutron stars colliding in circumstances different from the ones we have observed through gravitational waves. These collisions can compress matter to extremes that challenge our understanding of physics, creating brief, brilliant explosions. But again, the timing, colour and energy profile of AT2018 Cow didn't match any known pattern. Nature seemed to be improvising. As astronomers continued watching, a strange pattern emerged. AT2018 Cow was not an isolated event. Other flares with similar properties began to appear in new observations, each with fast rises, intense blue light, and rapid fades. These cousins were given names just as whimsical. Together they formed a new family of objects, fast blue optical transients. The name itself is a careful way of saying bright flashes that behave strangely and whose origins we do not yet understand. The growing group of these events widened the mystery. If they were truly a new phenomenon, then the universe had been performing this kind of cosmic flash for millions of years, yet our telescopes were only now sensitive enough to catch them. It raised a gentle question. How many other types of celestial events have been happening unnoticed, too quick or too faint for earlier generations of astronomers to detect? What is particularly soothing about this mystery is that it does not demand immediate answers. Unlike rare signals that happen once and never again, these fast blue transients now appear often enough that we can study them patiently. Patterns will emerge over time. We might learn how stars collapse under certain unusual conditions, or how compact remnants collide, or how matter behaves when pushed to extremes. We might discover that these flashes trace the lives of stars in small, quiet galaxies where interactions are rare, or perhaps they come from systems where the remnants of dead stars circle tightly, like dancers drawn together by gravity until one final, brilliant step. Whatever their origin, A2018 Cow and its kin remind us of a comforting truth. The universe is still full of firsts. Even now, with telescopes peering across billions of light years, and instruments sensitive enough to measure the faint glow of the early cosmos, nature continues to surprise us with events that defy our expectations. It is as though the sky sometimes saves a few chapters of its story for later, releasing them only when we have learned enough to notice. Fast blue transients do not roar like quasars or unleash waves like black hole mergers. They flicker quickly, like embers caught in a sudden gust. Their beauty lies in their brevity, and in the gap they open in our understanding. A gap wide enough to let curiosity flow through, and perhaps, as new telescopes come online, events like AT2018 Cow will become familiar. Perhaps the strange will become ordinary, or perhaps each new observation will reveal another layer of complexity. reminding us that the cosmos is not a closed book but a living one, always offering new passages to read. Most stars live long, quiet lives. They burn for millions or billions of years, shining steadily like lanterns in a dark valley. And when their time finally ends, they do so with a kind of cosmic dignity. Some collapse softly into dense remnants, others explode in spectacular supernovae whose bright light fades over weeks or months. These patterns have been studied long enough that astronomers can almost anticipate how a dying star should behave. But in the summer of 2018, the sky raised its hand politely and said, "Not always." The signal of this new event came from a galaxy about 200 million light-years away. Far, but not impossibly far. A telescope in Hawaii detected a sudden flare of light that was too bright, too fast and too blue to be anything familiar. Its official name, AT 2018 Cow, sounds almost playful, as if the universe were making a small joke. But the phenomenon behind the name was anything but ordinary. This flare did not brighten slowly like a supernova. It rose to its peak brightness in just a couple of days, like a match striking in the dark, and it wasn't merely bright by the standards of stellar explosions, it was tens of times brighter than common supernovae. Then, just as quickly as it rose, it began to decline. The whole event unfolded on a timescale that felt rushed, condensed, as though the universe had pressed fast forward instead of letting things play out in their usual rhythm. Imagine watching a firework, except instead of blooming and fading across a minute, it erupts and vanishes before you've even fully registered it. That is the feeling a 2018 Cow gave astronomers. It was too swift, too luminous, too strange. As soon as the light curve, the gentle rise and fall of brightness was recorded. Scientists started comparing it to everything in their catalogues. It did not match classical supernovae. It did not match gamma-ray bursts. It didn't match tidal disruption events caused by black holes shredding stars. It was as though the universe had briefly invented a new kind of explosion. One of the most striking qualities of the event was its colour. It was unusually blue, meaning it was extremely hot. The temperature of the explosion appeared to be higher than ordinary stellar blasts, as if the material was being heated by something incredibly compact and energetic. When astronomers studied how the spectrum changed over time, they noticed that the event cooled far more slowly than expected. Ordinary explosions expand and cool quickly. This one seemed to stay warm, its energy refusing to disperse. Something inside was pumping out power long after the initial flash. This led to the first hypothesis. Perhaps AT 2018 Cow marked the birth of a black hole or a neutron star. When a massive star collapses, its core can squeeze into something unimaginably dense. A neutron star packed as tightly as the nucleus of an atom, or a black hole whose gravity is so strong that even light cannot escape. The problem is that these objects normally hide behind the debris of the explosion, but in AT 2018 Cow, the debris seemed thin or perhaps blown outward rapidly, leaving the newborn object more exposed. It was as if the veil usually drawn across these final moments had been pulled aside, letting us glimpse a formation process that had only been theorized. Another idea suggested that the event might not have been a dying star at all. Instead, it could have been a smaller, compact star, something like a white dwarf, being torn apart by a black hole. In most tidal disruption events, the shredded material forms a luminous disk that emits ultraviolet and X-ray light. But in this case, the process would have to happen faster and more violently. The pace of the brightness changes suggested something unusually small and dense was involved. A black hole only a few times the mass of the Sun could, in theory, rip apart a white dwarf with terrifying efficiency, leaving behind a flash of light that rises and fades almost before we have time to name it. Yet another possibility involved collisions between compact remnants, perhaps a white dwarf smashing into a neutron star, or two neutron stars colliding in circumstances different from the ones we have observed through gravitational waves. These collisions can compress matter to extremes that challenge our understanding of physics, creating brief, brilliant explosions. But again, the timing, colour and energy profile of 802018 Cow didn't match any known pattern. Nature seemed to be improvising. As astronomers continued watching, a strange pattern emerged. 802018 Cow was not an isolated event. Other flares with similar properties began to appear in new observations, each with fast rises, intense blue light, and rapid fades. These cousins were given names just as whimsical. Together, they formed a new family of objects, fast blue optical transients. The name itself is a careful way of saying bright flashes that behave strangely and whose origins we do not yet understand. The growing group of these events widened the mystery. If they were truly a new phenomenon, then the universe had been performing this kind of cosmic flash for millions of years, yet our telescopes were only now sensitive enough to catch them. It raised a gentle question. How many other types of celestial events have been happening unnoticed, too quick or too faint for earlier generations of astronomers to detect? What is particularly soothing about this mystery is that it does not demand immediate answers. Unlike rare signals that happen once and never again, these fast blue transients now appear often enough that we can study them patiently. Patterns will emerge over time. We might learn how stars collapse under certain unusual conditions, or how compact remnants collide, or how matter behaves when pushed to extremes. We might discover that these flashes trace the lives of stars in small, quiet galaxies where interactions are rare. Or perhaps they come from systems where the remnants of dead stars circle tightly, like dancers drawn together by gravity until one final, brilliant step. Whatever their origin, 802018 Cow and its kin remind us of a comforting truth. The universe is still full of firsts. Even now, with telescopes peering across billions of light years and instruments sensitive enough to measure the faint glow of the early cosmos, nature continues to surprise us with events that defy our expectations. It is as though the sky sometimes saves a few chapters of its story for later, releasing them only when we have learned enough to notice. Fast blue transients do not roar like quasars or unleash waves like black hole mergers. They flicker quickly, like embers caught in a sudden gust. Their beauty lies in their brevity and in the gap they open in our understanding, a gap wide enough to let curiosity flow through. And perhaps, as new telescopes come online, events like 802018 Cow will become familiar. Perhaps the strange will become ordinary, or perhaps each new observation will reveal another layer of complexity, reminding us that the cosmos is not a closed book but a living one, always offering new passages to read. There is something quietly unsettling about perfect shapes in nature. The universe often prefers irregularity, clouds that billow unevenly, coastlines that refuse to be smooth, and nebulae that twist like smoke caught in a breeze. Even stars, which seem round from afar, wobble and flicker when watched up close. Perfect circles, especially on cosmic scales, are rare. So when astronomers saw a vast ring, so symmetrical it seemed almost drawn with a compass, hanging in radio images of the sky, they paused, and then they looked again. These structures were first spotted by a telescope in Australia, a wide-field array designed not to gaze at one small region of the sky, but to listen broadly, like someone cupping both hands behind their ears. In the early maps produced by this instrument, faint round shapes appeared, enormous circles glowing only in radio wavelengths. They were nearly invisible in optical light, quiet in infrared, and unremarkable in X-rays. But in radio, they stood out as clean, gentle halos, vast loops suspended in the darkness. Astronomers called them odd radio circles, though the name is more a confession than a label. Odd, because they were unlike anything seen before, radio because that was the only light they emitted, and circles because, astonishingly, that was exactly what they looked like. Not stretched, not lumpy, not fragmented. Just rings. To picture their size, imagine a sphere so wide that entire galaxies sit comfortably inside it. Some of these circles span hundreds of thousands, perhaps even more than 1 million light-years across. If our entire Milky Way were laid inside one, it would look like a tiny coin resting inside a massive crown. That scale alone suggests something extraordinary happened to produce them, something powerful enough to leave a mark larger than most galaxy clusters. At first, astronomers wondered whether these rings were simply remnants of supernova explosions. When a star dies in a violent burst, the shock can leave behind a shell of radio-emitting gas. But those shells are far smaller, often just a few dozen light-years wide. Odd radio circles are 1,000 times larger. They're too big to be the ghosts of dying stars. Perhaps they were the result of jets fired from the hearts of active galaxies. Black holes that feed greedily can produce enormous radio lobes, blossoming plumes of charged particles that stream into space for millions of years. These lobes can be sprawling, magnificent arcs of light, but even they rarely form perfect rings. And crucially, the galaxies at the centres of odd radio circles do not appear to be active. They look ordinary, calm, even quiet. No blazing nucleus, no energetic jets. Nothing to suggest they recently unleashed enough force to sculpt a ring 500,000 light-years wide. Another idea. Maybe these were bubbles created when two galaxies collided long ago, sending out a shockwave that wrapped around them in a slow-moving ripple. But those events leave behind signatures, stretched stars, messy debris, disrupted gas that astronomers know how to recognize. Odd radio circles show no such scars. The question deepened. How does one create a circle so large, so clean? There is something haunting about the symmetry. Natural cosmic structures almost always show signs of turbulence. Places where clouds merged unevenly, where gravity twisted matter, where magnetic fields tangle themselves like thread in a child's pocket. Odd radio circles feel almost too tidy. It's as though some vast event puffed outward with such precision that the edges cooled evenly, forming a smooth, glowing boundary while the interior remained dark. One suggestion is that these circles mark the aftermath of enormous shockwaves, the kind that might ripple outward when something deeply powerful occurs at a galaxy's core. Imagine a stone dropped in a still lake. Not a small stone, but one the size of a mountain. The ripple would be immense, expanding in all directions with perfect symmetry. But instead of water, these ripples travel through space itself, leaving behind shells of energized particles. If a galaxy experienced a sudden outburst, perhaps from a merger, perhaps from a rare period of hyperactive black hole feeding, the shock could, in theory, create a ring. Yet the galaxies inside the circles do not look like veterans of such violent pasts. They appear surprisingly ordinary. No distorted shapes, no giant scars, just regular elliptical galaxies sitting quietly at the centre of perfect rings. Another theory steps further back in time. Instead of thinking about what happened recently, we imagine what may have happened billions of years ago, when the universe was younger and its rules more fluid. Some physicists suggest these rings might be the signatures of cosmic strings, hypothetical cracks in space-time itself, formed in the earliest moments after the universe's birth. If two such strings collided or vibrated, they could produce immense bursts of energy, leaving behind circular shock patterns. But cosmic strings remain theoretical, like footprints without a confirmed creature to match them. It is equally compelling to imagine these rings as the remnants of events we have not yet conceived. Nature has surprised us before. Pulsars, quasars, and gamma-ray bursts were all discovered long before we understood what they were. Perhaps odd radio circles belong to this same category, a phenomenon waiting patiently for the right instruments, the right theories, the right questions to illuminate its origin. Just as intriguing as their shape is their number, only a handful of odd radio circles have been found so far. Not dozens, not hundreds, just a small collection, scattered faintly across the sky. This scarcity adds to the mystery. If the process that creates them is common, we should see more. If it is rare, then the few we have found might be precious windows into a mechanism we only faintly glimpse. Their faintness also hints at something gentle despite their size. They glow softly, not brightly. They do not roar with energy. They hover, quiet and diffused, like the lingering outline of something that happened long ago. They remind us that not all cosmic events need to be violent in the present to have been powerful in the past. Some echoes only whisper long after the initial sound has faded. What is most soothing about odd radio circles is the patience they demand. These structures will persist for millions of years. We are not rushing against time to understand them. We can approach them slowly, letting each new observation add a small brushstroke to the picture. Their mystery does not shout. It rests gently, like a ring of smoke drifting above a fire long extinguished. And perhaps that is why they enchant so many astronomers. They are the quiet anomalies, the ones that don't demand attention but reward curiosity. They are reminders that the universe is still full of geometry we didn't expect, symmetry we cannot yet explain, and events so ancient that only their softened outlines remain. When you look at the night sky, most of what you see feels scattered. Stars sprinkled in loose patterns, galaxies drifting through cosmic space with no obvious symmetry. Even on the largest scales we can measure, the universe resembles a sprawling web. Filaments of galaxies stretching like threads, clusters forming knots, and vast empty spaces lying quietly between them. It's intricate, yes, but it's also messy, chaotic, natural. So when astronomers discovered a structure that seemed to carve a gentle, graceful curve across billions of light years, they felt something unusual, quiet disbelief. Not the kind that comes with shock, but the softer kind. The kind you feel when walking along a beach and finding a stone shaped too perfectly to have been formed by chance alone. This curve, now known as the giant arc, spans roughly 3.3 billion light years, an expanse so large that light travelling at the universe's maximum speed would still need billions of years to cross it. To imagine its scale, picture stretching a ribbon of galaxies across 1/15 of the visible universe. The structure doesn't resemble the tangled filaments that normally make up the cosmic web. Instead, it sweeps across the sky like the faint outline of a bow or an arc drawn with deliberate care. The discovery began not with a dramatic explosion or a sudden flash, but with an astronomer sifting through galaxy maps, large catalogues listing the positions of hundreds of thousands of distant objects. These maps act like star atlases on cosmic scales, helping us trace how matter clusters across space. As the data was examined, a pattern began to emerge. Galaxies that should have been randomly positioned instead gathered along a smooth curve. First a hint, then a shape, then a structure too coherent to dismiss. The giant arc doesn't glow like a nebula or pulsing star. It consists of quiet galaxies, normal galaxies, in a pattern that should not exist naturally at that size. It is the arrangement, not the brightness, that captures attention. To understand why this arc feels so implausible, consider how cosmic structures grow. In the early universe, matter was spread almost evenly, with tiny ripples, small variations in density that you could imagine as gentle wrinkles on a sheet. Over billions of years, gravity tugged on those wrinkles. Some regions pulled more matter toward them, becoming filaments and clusters. Others emptied out, growing into vast voids. But this growth has limits. Gravity can only stretch these arrangements so far before cosmic expansion. The slow spreading of space prevents structures from becoming too large. Our modern cosmological models, built carefully from decades of observations, predict that the largest gravitationally grown structures should reach maybe 1 billion light-years. Some might push slightly beyond that. But 3.3 billion? That lies far outside the expected range. Not impossible in the strictest mathematical sense, but so improbable that calling it a coincidence requires a deep, almost blind trust in randomness. Astronomers estimated the odds of such a pattern appearing by chance. Their answer, spoken softly and with caution, was that the probability is extremely low, perhaps a few chances in several thousand. Not impossibly rare, but rare enough to make you pause, the way you would if you found two seashells on opposite sides of the ocean with matching spirals. It could happen, but it asks for reflection. Some scientists wondered whether the giant arc might simply be an illusion created by incomplete data. Perhaps the galaxies only appeared to form a curve, their arrangement exaggerated by the way we draw our maps or select our samples. But further checks reinforced the structure's reality. Even with different data and different methods, the arc persisted, like a gentle signature written across the sky. This curve challenges something fundamental, the cosmological principle. This principle, softened gently, is the idea that the universe looks roughly the same no matter where you stand or which direction you look. On large enough scales, no region should be special. No direction should be marked by unusual patterns. Everything should blend into a statistical uniformity, quiet, even, predictable. But the giant arc hints that the universe may be more textured than we assumed, more patterned. Not in a neat, architectural sense, but in the sense of a handmade quilt, where occasional stitches align in ways that reflect the motions of the hands that made them, not the rules we thought they followed. If the giant arc is real, and the evidence says it is, then something in the early universe nudged matter into this long, elegant curve, something beyond the tiny fluctuations we usually imagine, something that stretched across enormous distances before galaxies were even born. Perhaps it was an especially large ripple in the universe's newborn fabric. Perhaps it was a long, gentle wave in the primordial plasma before atoms formed, or perhaps it hints at some new influence, something not yet named, that shaped space itself. It's important to say this gently. Nobody believes the giant arc rewrites all of cosmology. It's one strange structure among many, but it is strange enough to make us listen. It asks us to imagine the early universe not as a simple soup, but as a place with grains, subtle lines and curves that later evolved into patterns we now observe. One of the most soothing aspects of this mystery is that it isn't going anywhere. The arc is not fading or exploding. It's a fossil, an ancient arrangement frozen in place, waiting patiently for us to understand it. New instruments, especially next-generation galaxy surveys, will soon map the sky in far greater detail. They may reveal more arcs, or rings, or crescents, patterns that hint at forces we do not yet know how to describe. For now, the giant arc is a quiet, elegant contradiction, a curve too large for our models, too coherent to ignore, too soft to demand immediate answers. It sits across the sky like a question written in gentle handwriting, reminding us that the universe is bigger, older, and more surprising than our theories often allow. And sometimes, all it takes is one curve, one unexpected stroke on the cosmic canvas, to remind us how unfinished our understanding truly is. When astronomers first traced the curve of the giant arc across the sky, it felt like discovering a brushstroke from an unknown cosmic painter. But just as the community was still absorbing that surprise, another shape quietly emerged from the data, one even more deliberate, even more symmetrical. While the giant arc stretched like a bowed line across billions of light years, this new structure curled inward, forming a loop, a ring, a nearly perfect circle made not of light or gas, but of galaxies themselves. It came to be known as the Big Ring, and its discovery deepened the sense that the universe still holds patterns we have not yet learned to recognize. Think of the Big Ring as a chain of galaxy clusters arranged in a circular pattern about 1.3 billion light-years across. That distance is difficult to grasp. If you were to imagine the Milky Way placed inside this structure, there would be enough room for dozens more galaxies of similar size to sit comfortably side by side, all arranged in a loop vast enough to challenge imagination, like a quiet halo carved into the cosmic web. The discovery emerged from the same region where the giant arc was found, an overlapping patch of the distant universe, and that coincidence alone made astronomers pause. Two enormous, improbable structures appearing so close together on the sky. It felt less like a random scatter and more like a subtle motif repeating itself, as though the universe were humming a melodic phrase across billions of light years. To understand why a ring is surprising, we need to step gently into how cosmic structure usually forms. When the universe was young, matter began to clump under gravity. But the clumping wasn't uniform. It stretched into filaments, long strands of galaxies bound together like threads. At the intersections of these threads, galaxy clusters formed, heavier and denser like knots in a tapestry. Between them lay voids, bubbles of near emptiness where matter drifted away instead of collecting. This pattern, the cosmic web, is beautiful in its complexity. But it rarely arranges itself into tidy shapes. Straight lines, careful arcs, and perfect circles are not part of its usual vocabulary. Rings require a mechanism that sculpts matter outward in all directions from a central point and leaves a thin border behind. In small environments, things like supernova, shock fronts, or expanding bubbles of gas can form circular features. But nothing in known physics creates ring shapes spanning roughly 1 billion light-years. Yet here, in this single patch of cosmic sky, galaxies appear to trace such a shape. Not precisely, not like ink on paper, but enough that the human eye, and the trained algorithms of astronomers, can see a looping outline that is difficult to dismiss. Some researchers wondered whether the Big Ring might be an illusion caused by the way distances are measured. When objects lie at different depths along our line of sight, they can appear to form patterns that aren't truly circular. But the careful measurements used in this study relied on redshift, the soft stretching of light as galaxies drift farther from us with cosmic expansion. This method, when applied carefully, gives a reasonably reliable estimate of distance. And even after adjusting for uncertainties, the ring remained. Why should galaxies arrange themselves this way? One idea is that both the giant arc and the Big Ring might be different expressions of the same ancient influence, some large-scale ripple or wave in the early universe that guided matter along sweeping curves. It's a poetic idea, imagining the infant universe as a pool of warm plasma where gentle waves travelled outward, freezing into patterns that billions of years later became galaxies and clusters. Another idea ventures into deeper speculation, considering whether the early universe could have contained topological features, shapes imprinted on the fabric of space itself. These features, if they existed, could channel matter in unusual ways, creating rings or arcs as the universe expanded and cooled. But this possibility remains soft and untested, like a sketch drawn on the edge of a notebook. Then there are even more subtle explanations. Perhaps the big ring is not truly a ring, but the cross-section of a spiral structure, similar to looking at a coil of rope end-on. Or maybe we're seeing only the brightest parts of something larger and more irregular. The universe is vast and our view is partial. Light takes billions of years to reach us, and dust, distance, and dimness shape what we perceive. Yet even with these uncertainties, the big ring carries a sense of intention. It feels like a cosmic gesture, the kind a river makes when it bends gracefully around an unseen stone. Gentle, unforced, but unmistakable. What makes this discovery even more charming is its proximity to the giant arc. Their closeness deepens the mystery. If both structures are real and not statistical coincidences, then this region of the universe might hold clues about conditions in the early cosmos, clues about how matter flowed, clustered, and cooled, clues about whether our understanding of cosmic uniformity, this idea that the universe should look roughly the same everywhere, is too simple. The standard cosmological principle says that when you zoom out far enough, the universe becomes smooth. Patterns disappear, but the big ring refuses to disappear. It sits there, gently defying expectations, a soft circle carved from the distribution of galaxies. And perhaps the most calming part of this mystery is its patience. Like the giant arc, the big ring is not going anywhere. It has existed for billions of years. It will exist for billions more. It does not require urgent explanation. It can wait for us to refine our tools, deepen our models, expand our surveys, and soften our assumptions. In that sense, the big ring becomes less a puzzle and more a companion, an old quiet shape shining softly from across the cosmos, reminding us that the universe is not a finished picture. There are still patterns hidden in the dark, still shapes waiting to be traced, still melodies written into the stars that our ears have not yet learned to hear. When we picture the universe, we often imagine it filled with stars, galaxies, nebulae, and swirling clusters, an endless expanse of light suspended in a dark sea. But the cosmos is not made only of crowded places. It is also made of hollows, of immense regions where almost nothing resides. And among all these hollows, one stands apart in its quiet vastness, the Boötes Void. A bubble so empty that the universe seems to take a gentle breath there. To understand the Boötes Void, imagine the cosmic web as a three-dimensional lattice, a network of filaments where galaxies cling like dewdrops on strands of a spider's web. Most of the universe follows this pattern. Bright knots of galaxies gather at intersections. Filaments stretch between them like glowing bridges. Even the empty parts usually contain a sprinkle of lonely galaxies drifting through space. But the Boötes Void breaks this rule in the softest, most astonishing way. It is a small, about 330 million light-years wide. If you place the Milky Way inside it, you could travel for countless generations before encountering a neighbouring galaxy. It is a cavern in the universe's structure, a hollow so wide that light itself seems to hesitate as it crosses. Based on everything we know about how matter clusters, such a region should hold around 2,000 galaxies. That is what our models, gently simplified, would predict for an area of that size. Yet when astronomers first surveyed it, they counted not thousands, not hundreds, but only 60 or so. A number so small that it feels like a whisper inside a room meant for a choir. It is this contrast, not absolute emptiness, but unexpected emptiness, that gives the Boötes Void its quiet mystery. The galaxies that do reside inside the void behave differently from their cousins in denser regions. Without the gravitational influence of nearby galaxies, they evolve in isolation, almost like plants growing alone on a wide prairie. Some seem oddly shaped. Some show bursts of star formation that appear more intense than expected, A few are stretched or twisted in subtle ways, as if shaped by the silence around them. Isolation, in the universe as in nature, often leads to unusual growth. So how does such a massive hollow form? The leading idea traces back to the very beginning of the cosmos, when the universe was newborn and filled with gentle fluctuations, tiny differences in density no thicker than wrinkles on the surface of warm milk. Over time, as the universe expanded, these wrinkles were stretched and magnified. Some became dense regions where galaxies later formed. Others became sparse regions where matter drifted away instead of collecting. The Boötes Void, in this view, may be the result of one such early wrinkle, a small underdensity that, over billions of years, widened into a great hollow. It is comforting to imagine it this way, a soft imperfection in the fabric of the young universe, slowly unfolding into a vast bubble. Yet even with this explanation, the Boötes Void seems to sit near the limits of what our models consider likely. Not impossible, but uncomfortably large. A void so vast that it nudges the edges of our theories, reminding us that nature might weave its patterns a bit more boldly than our formulas predict. Some astronomers propose that the void may not be a single hollow at all, but the result of several smaller neighbouring voids gradually merging, like soap bubbles coalescing into a larger chamber. If so, the Boötes Void may be a mosaic of emptiness, a region shaped not by one event but by many overlapping waves of underdensity. This idea softens the mystery slightly but does not erase it. Others suggest that the void may influence our observations in subtle ways. Light travelling through such an underdense region may stretch or shift more than expected, potentially affecting how we infer distances or motions. In this sense, the Boötes Void becomes not only a structure to observe but a lens, one that bends our understanding gently but noticeably. This idea connects to a broader theme in cosmology. Emptiness itself can be a clue. Regions with too little matter can reveal as much about the universe as regions with too much. They help us understand how gravity shapes the cosmic web. They help us check our assumptions about dark matter and dark energy. They help test whether the universe behaves the same everywhere, or whether some neighbourhoods, like this one, carry echoes of unusual beginnings. But perhaps the most soothing aspect of the Boötes Void is simply its presence. It is an enormous, quiet place. A cosmic cavern whose existence feels almost meditative. It does not roar with radiation or burst with star formation. It simply is a vast breath held within the universe. Some scientists, when first contemplating its scale, joked gently that if the Milky Way lived inside such a void, our night sky would be nearly empty. We would look up and see only a few scattered stars, never realizing that the universe beyond our hollow was bright and crowded. The thought is humbling. So much of what we know about the cosmos depends on where we stand. And in a soft philosophical way, the Boötes Void reminds us that silence has shape. That emptiness, too, can carry meaning. It is not just the places where galaxies gather that matter. It is also the places where they do not. The void teaches us that absence can be a presence of its own, a reminder that the universe is not uniformly filled, not entirely predictable, and certainly not finished revealing its deeper patterns. It also sets the stage for the next mysteries, the other voids surrounding us, the behaviour of galaxies near the edges of these hollows, and the strange disagreements in how we measure the universe's expansion. The Boötes Void is only one quiet chamber in a much larger structure of cosmic emptiness, and like all good mysteries, it waits patiently, large and silent, for us to understand its story. The Boötes Void is vast, so vast that it feels almost like the universe exhaling, but it is not alone. Our cosmic neighbourhood, though far smaller in scale, contains its own hollows, each one shaping the motion of galaxies in subtle ways. These quiet places are the local void and the KBC void, regions where matter thins out gently, like soft pockets in the cosmic fabric. And in studying them, astronomers have discovered something puzzling, something that echoes through modern cosmology, like the faint chime of two clocks ticking at slightly different speeds. To understand these nearby voids, imagine standing on a hillside and looking down into a wide valley. Most galaxies lie along the ridges and slopes of the cosmic landscape, where matter has pooled over billions of years. But we, in the Milky Way, sit close to the edge of a shallow valley, not as empty as the Boötes Void, not as dramatic, but unmistakably a low-density region. This is the local void. If we could drift above our galaxy and paint matter density as shades of blue and red, blue for sparse regions, red for crowded ones, the area just beside our home would glow a soft, gentle blue. There simply aren't as many galaxies there, and that emptiness has consequences. Gravity works like a network of invisible threads. Regions with more matter pull gently on galaxies, drawing them inward. Regions with less matter tug less. Because the local void contains so little mass, it exerts almost no pull on the Milky Way. Meanwhile, denser regions on the opposite side apply a stronger tug. This imbalance creates a subtle push, nudging our galaxy ever so slightly toward richer clusters. In everyday terms, living beside a void is like standing near the edge of a quiet, windless prairie, while a lively, bustling town lies on the other side. Even without thinking, you feel the pull of activity, the draw toward where things gather. Nature tends to drift toward fullness. The KBC void, named after the astronomers who first measured it, lies farther away, but it is much larger. It spans hundreds of millions of light years, shaping how galaxies within and around it move. We may not live inside this void, but we feel its influence the way you might feel the emptiness of a large room even while standing near the doorway. The surrounding matter responds to it, flowing gently around its edges. These voids matter not only because of their emptiness, but because of what they reveal about the expansion of the universe. For more than a century, astronomers have measured how fast galaxies move away from us. This expansion rate, softened, we can call it the speed at which space slowly stretches, is described by a number known as the Hubble constant. But here is the puzzle. Different methods of measuring this constant give different answers. One technique looks at nearby galaxies and their bright standard candles, stars whose light acts like a steady lantern. Another measures faint ripples in the universe's earliest light, the cosmic microwave background. These two methods should agree, like two clocks keeping time together. Instead, they differ, slightly, persistently. Enough that the discrepancy has become one of the biggest mysteries in cosmology. A gentle disagreement between cosmic clocks. Living near a void complicates this picture. If our neighbourhood contains less matter than average, then galaxies near us might drift a little faster than expected, just as a ball rolls more quickly when it begins its motion near the edge of a hill. This extra outward drift could make the local expansion rate appear larger than the global one measured across billions of light years. Some scientists have suggested that the local void and the KBC void could explain part of this disagreement. Perhaps the universe's expansion looks inconsistent only because we are standing in an unusually quiet place, a region with fewer gravitational anchors. But as soothing as this idea is, it does not resolve the puzzle entirely. The voids help, but they do not close the gap between the competing measurements. At best, they soften the disagreement, they do not eliminate it. It is like discovering that one of your clocks sits on a slanted table. Yes, it might tick oddly because of the incline, but even after you level it, the clocks still don't perfectly agree. This leaves us with a gentle tension, a feeling that something deeper may be stirring in the background. Perhaps the methods themselves contain tiny errors that we have not yet learned to recognize. Perhaps the early universe behaved slightly differently than our models assume. Perhaps space expands in ways that are subtly more complex than a single number can easily summarize. Or perhaps something truly new waits just beyond our current understanding. Voids, in this context, become more than empty places. They become laboratories, quiet rooms, where the universe reveals its subtle behaviours. By studying how galaxies move near the edges of these hollows, astronomers can test theories of gravity, dark matter, and cosmic expansion. They can also refine the techniques used to measure distances and velocities across unimaginable scales. The local void, in particular, gives us a comforting sense of perspective. It reminds us that our galaxy is not at the centre of anything. We do not live in a privileged or overly dramatic location. We live near a gentle hollow, a region where the universe whispers rather than shouts, and perhaps that is fitting. Our own planet is an oasis of calm in a universe filled with extreme forces and luminous storms. That we should also live near a cosmic quiet zone feels almost poetic. As we turn from the nearby voids to the much older mysteries imprinted in the cosmic microwave background, the tension between different measurements continues to follow us like a soft echo. It is neither alarming nor urgent. It is simply a sign, a reminder that we are still learning the shape of the cosmic landscape, and like all landscapes, it contains hills and valleys, clusters and hollows, crowded places and places where almost nothing stirs. Long before galaxies formed their swirling spirals and stars began to shine, the universe was wrapped in a warm glowing fog, a soft afterglow from its earliest moments. Today that ancient light reaches us as a faint microwave hum coming from every direction. Astronomers call it the cosmic microwave background, but it can be described more gently as the fading warmth left over from the universe's newborn age. It is one of the quietest and most important signals we have, carrying memories from nearly 14 billion years ago. Most of this ancient glow is uniform, like the even warmth of a gentle bath. There are tiny variations, slight warm spots and slight cool spots, each only a few millionths of a degree different from the average. These small variations are normal. They are the fingerprints of the young cosmos, marks that eventually grew into galaxies and clusters. But among them lies one region that stands out, a patch in the southern sky that is noticeably cooler than expected. It is known, softly and simply, as the cold spot. At first glance, the cold spot is not dramatic. It does not shout with colour or brightness. It does not pulse or flare. It is just a wide, faintly cooler region, roughly circular, spanning an area much larger than the moon would appear in our sky. Yet its existence has puzzled astronomers for more than 2 decades, because the universe's earliest light should not have produced such a feature by chance alone. To imagine what the cold spot is, picture a glowing ember slowly fading as it cools. Now imagine one part of the ember dimming more than the rest, as though a breeze has brushed across it. That kind of uneven cooling is what we see in this region, subtle but persistent, a whisper of something unexpected. The most straightforward explanation involves a large, sparse region of space lying between us and the cold spot, what astronomers call a super void. Light loses a tiny bit of energy when it travels through emptier than usual regions. It is not because the void takes something from the light, but because space itself stretches more gently there. As light climbs out of these wide, thin valleys, it arrives slightly cooler. This soft effect, translated gently from technical language, is known as a gravitational energy loss along the journey. But there is a problem. The supervoid we have mapped in that direction exists, but it is not large or deep enough to explain the full cooling we observe. It is like noticing a ripple in a pond and discovering that the stone nearby is far too small to have caused it. The void helps, but it does not solve the puzzle. And so, the cold spot remains unusual, an old question written into the universe's first light. Some scientists have explored more speculative possibilities, spoken carefully and without sensationalism. One idea imagines that the universe in its earliest moments may have contained bubbles, regions with slightly different initial conditions. If two such bubbles brushed against one another, they might have left a faint mark on the cosmic microwave background, a bruise in the fabric of ancient light. The cold spot in this view might be a memory of a very early collision between two expanding regions of space. Another idea imagines deeper wrinkles in the young universe's structure, perhaps formed by rare fluctuations in its earliest plasma. These fluctuations could have stretched into unusual patterns as the cosmos expanded, leaving behind cooler regions in the afterglow. This is less dramatic than a bubble collision, but no less poetic, like a crease in ancient parchment that persists even after centuries. It is essential to speak of these possibilities gently. They are not conclusions, they are reflections, attempts to explain a feature that sits near the edge of our comfort with statistics. Many scientists believe the cold spot could still be a coincidence, a rare but natural outcome of random temperature variations. After all, if you scatter pebbles across a field, one area will always look emptier than the rest, even if no one arranged it that way. Yet, coincidences this large always feel a bit strange. That is the heart of the mystery. What makes the cold spot so compelling is not that it contradicts our understanding of physics, but that it nudges it. It whispers that maybe, in the earliest moments of the universe, space behaved in ways we have not fully understood. Or perhaps our models of how light drifts through voids need subtle adjustments. Or maybe our cosmic map still holds shadows where our data remains incomplete. The cold spot also reminds us of the quiet power of modern instruments. Satellites such as COBE, Unanswered, and Planck were not built to capture fireworks or explosions. They were built to listen to the universe's faintest memory, a glow only a few degrees above absolute zero. The fact that they can detect differences as small as tens of millionths of a degree speaks to the extraordinary gentleness of our modern tools. Tools that treat the sky not as a canvas to stare at, but as a whisper to be heard. Even more comforting is the realization that the cold spot is not something temporary. It will not vanish or flare. It will remain as it is, quietly embedded in the cosmic afterglow, waiting for new theories and deeper maps to someday clarify its story. It is patient. Older than any star, older than any galaxy, older than all of human history combined. Perhaps the most poetic aspect of the cold spot is the way it frames emptiness. Instead of thinking of emptiness as lacking something, the cold spot encourages us to see emptiness as a place where subtle stories unfold, where light loses a bit of its warmth, where early cosmic conditions leave gentle imprints, where the universe's ancient breath cools just slightly differently. And like so many anomalies in the cosmos, the cold spot does not demand certainty. It invites curiosity. It asks for humility. It suggests that even after decades of observing the sky, we are still students of the universe, still learning to interpret its quiet signatures. When we trace our gaze across this chilly region of ancient light, we are looking at a message older than every star we have ever studied. A message written in the universe's first language, printed not in ink but in temperature. A message that reads, softly, "There is more here than you yet understand." In the great cosmic web, galaxies usually gather like fireflies attracted to an unseen lantern. That lantern, according to decades of observations, is dark matter. the invisible mass that wraps around galaxies, holding their stars together with a gravitational embrace. Without it, stars would drift away like dandelion seeds in a breeze. So when astronomers found galaxies that seemed to contain almost none of this unseen glue, the discovery felt like meeting a bird that somehow flies without feathers. Not impossible, but deeply unexpected. To understand why this is so strange, it helps to picture what a typical galaxy looks like beneath the visible stars. Imagine pouring a handful of glowing dust into a thick, transparent syrup. The dust represents the stars, and the syrup represents dark matter. Even though you cannot see the syrup, it supports and shapes the dust, keeping it in a loosely spherical cloud. Without the syrup, the dust would scatter. That is how dark matter works, silently shaping galaxies from within. Most galaxies, from sprawling spirals to tiny dwarfs, contain far more dark matter than ordinary matter, often 10 times more, sometimes even more than that. This is why the motions of stars inside galaxies make sense. They orbit quickly but do not fly apart because the galaxy's hidden mass holds them in place. So imagine the surprise when astronomers found galaxies whose stars move so gently, so slowly, that the invisible syrup seems almost absent. 2 early examples, discovered only in the last decade, showed motion so calm that dark matter appeared to be barely present. Later, more candidates emerged, each one challenging the idea that dark matter is universal and uniform. If these galaxies truly lack dark matter, then their stability becomes a soft puzzle. Their stars drift at speeds too low to require extra invisible mass. They behave almost like small clouds of stars just loosely floating together. This should not be possible under traditional galaxy formation theories, which rely on dark matter halos as the seeds around which gas gathers to form stars. Without these halos, galaxies should not form at all. One idea is that these galaxies truly started with dark matter but later lost it. Perhaps powerful winds from supernova explosions pushed gas and stars outward, leaving the dark matter behind. But this scenario requires a delicate coordination of forces, almost like asking a storm to remove every leaf from a tree but none of the branches. It is difficult, but not impossible. Another possibility is that these galaxies formed in unusual tidal environments, places where gravity from nearby massive galaxies stretched and pulled them apart. If a galaxy is torn repeatedly by gravitational tides, it could, in theory, lose much of its dark matter, like a seashell slowly worn down by waves. But again, this requires very specific conditions. A third idea is that these galaxies do have dark matter, but it is arranged differently, spread so widely that it barely affects the speed of their stars. In this view, the syrup is still there, just thinned out, like warm honey spread over a plate instead of gathered in a bowl. But even this interpretation struggles to explain all observed cases. And then there is a more radical interpretation, spoken quietly, as all bold ideas should be. Perhaps our understanding of dark matter itself is incomplete. Maybe not all galaxies rely on the same invisible substance. Or maybe gravity behaves differently in extremely sparse environments. These thoughts are not mainstream conclusions, nor should they be, but they remind us that anomalies sometimes point toward deeper laws waiting to be discovered. What makes these galaxies especially soothing to contemplate is their visual appearance. Many belong to a class called ultra-diffuse galaxies, objects that have the size of the Milky Way but contain only a fraction of its stars. They resemble faint smudges like ghostly footprints across the sky. Through a telescope, they appear as delicate glows with no bright core, no swirling arms, just a soft wash of starlight stretched thin over a vast region. Some astronomers liken them to cosmic thistles, wide, airy, and surprisingly fragile looking. Others compare them to lanterns whose flames burn low, illuminating only the faintest outline of their shape. Their very existence feels gentle, almost meditative. The surprising part is that galaxies with too little dark matter do not all look alike. Some are faint and diffuse. Others are surprisingly bright and compact. Some lie near much larger galaxies, as though influenced by their neighbours. Others drift alone in the quiet outskirts of galaxy clusters. This diversity makes the mystery more textured. It suggests that there may not be a single explanation but a family of them, a collection of pathways by which galaxies can grow light in dark matter. As we explore this strange class of galaxies, new questions arise. Could some galaxies have formed from pure gas expelled during violent encounters between larger galaxies? Could others be remnants of colliding systems, reshaped in ways we do not yet fully understand? Could still others be temporary arrangements, fleeting collections of stars that will eventually drift apart? What comforts many astronomers is that these galaxies are not threatening the foundations of cosmology. They are not contradictions, they are opportunities, gentle reminders that the universe contains exceptions to nearly every rule we write. And exceptions are precious. They force us to revisit our assumptions, refine our theories, and imagine new possibilities. Dark matter itself remains one of the deepest mysteries in modern science. We feel its gravitational pull, we infer its presence, but we have never touched it, seen it, or directly measured it. It behaves like a shadow that shapes everything, yet reveals nothing of its own nature. When galaxies appear to defy its influence, those shadows shift slightly, inviting us to look again with fresh eyes. The galaxies with too little dark matter do not scream with cosmic violence. They do not announce themselves with explosions or brilliant light. They simply exist, quiet, faint, drifting on gentle orbits. Their stories unfold slowly, giving the scientific community time to think, to question, and to follow each clue patiently. And perhaps that is their greatest gift. They show us that the universe is not bound to a single pattern. It plays variations. It improvises. It creates galaxies that are heavy with unseen mass, and galaxies that seem almost weightless. In doing so, it invites us to let go of rigid expectations and embrace the idea that cosmic order is richer and more nuanced than we imagined. These delicate galaxies, faint as soft lanterns, remind us that sometimes the universe whispers its insights rather than shouting them. As we journey through the cosmos, each mystery seems to stand on its own, like a solitary stone resting on a quiet path. A strange dimming star here, an impossible visitor streaking through the solar system there. A ripple of radio waves lasting only 1,000th of a second. A galaxy missing most of the invisible matter it should carry. A ring of galaxies too large to explain. A hollow in space so wide it feels like a cosmic breath. Individually, each anomaly is intriguing. But when you step back, gently, thoughtfully, they begin to resemble knots in a tapestry, threads that seem unconnected until you notice how they tug at similar patterns. They start to echo one another, not in what they are, but in what they imply. That our picture of the universe, beautiful as it is, may still be missing a few strokes. This session is a chance to pause and gather these threads, letting the echoes overlap softly, like notes blending into a larger cosmic song. Consider first the anomalies of light and signal, the wow signal, the curious flickering of Tabby's star, the fleeting murmurs of fast radio bursts. All of these challenge our understanding of how energy behaves in space. Some seem too clean, too focused, or too abrupt to match simple natural processes. They urge us to refine our models of stellar environments, plasma physics, and the subtle ways light interacts with matter, they remind us that the cosmos speaks not only in grand explosions, but also in short, delicate pulses. Now set these alongside the anomalies of structure, the giant arc stretching across billions of light years, the big ring looping gently in the distant sky, the Boötes Void yawning like a cavern in the cosmic web, and the cold spot lingering in the universe's first light. These are not small curiosities. They are grand, sweeping features that challenge our assumptions about how the universe arranges its matter. Their sheer scale hints that something about the early universe may have operated differently than we currently imagine. Perhaps the initial ripples in the fabric of space were more varied, more textured, or more coherent than our models assume, and then consider the anomalies of matter itself. Galaxies with barely any dark matter, stars laden with short-lived radioactive elements, objects like Oumuamua, whose shapes and motions resist simple categorization. Each of these raises questions about the nature of the building blocks of the universe, the forces that bind stars, the processes that shape planets, the invisible mass that governs motion on galactic scales. Taken separately, they are surprises. Taken together, they feel like gentle reminders that the universe still has chapters we have not yet read. History shows that anomalies often precede breakthroughs. Think of Mercury's orbit, which stubbornly refused to match predictions until Einstein revealed the curvature of space-time. Think of quasars, once mysterious points of impossible brightness, later understood as black holes feeding in distant galaxies. Consider the discovery of the universe's accelerating expansion, which introduced the idea of dark energy, a concept still wrapped in mystery. Before each leap forward, nature presented a puzzle that did not fit, a tension, a gentle contradiction, and only by facing these contradictions, patiently, skeptically but open-mindedly, did understanding grow. The current anomalies echo this pattern. They are not failures of science. They are signs that science is alive. It is tempting to imagine connections between them, to wonder whether the same unknown ingredient could explain the giant arc, dark matter-poor galaxies, bizarre stellar chemistry, and the cold spot. Perhaps one underlying principle ties them together, like a single melody played on different instruments. Maybe the early universe imprinted subtle rhythms on matter that we are only now beginning to perceive. Maybe gravity behaves differently in extreme environments. Maybe dark matter is more complex than a single invisible substance. Or perhaps space-time itself carries structures we have not yet learned to name. But we should tread gently here. The history of science reminds us that not all puzzles share the same origin. Many anomalies will eventually find ordinary explanations. Dust where we thought there was none. Interactions too subtle for previous instruments to detect. Measurement uncertainties slowly refined by better technology. Nature is patient and often simpler than our imagination. Still, some mysteries endure, and it is these enduring ones that reshape our understanding. What makes this session comforting is that the echoes do not point toward chaos. They point toward refinement, toward growth, toward the idea that our models are good but not perfect, like maps drawn by candlelight, capturing the major features while leaving small details for later explorers. And we are those explorers. Imagine the universe as a vast library. Each anomaly is a book pulled slightly from the shelf, its spine catching your eye. The more books that sit askew, the more you suspect there is a section you have not yet discovered. Not a contradiction, but an invitation. The echoes also remind us of humility. The universe does not owe us simplicity. It does not unfold its mysteries in neat sequences. Sometimes it reveals a puzzle in the behavior of a single distant star. Sometimes it reveals one in the arrangement of galaxies stretched across billions of light years. Sometimes it reveals one in a small disagreement between two methods of measuring the same quantity. All of these whispers say the same thing: keep looking. And in that sense, anomalies are gifts. They keep science from becoming still. They offer resistance that sharpens understanding. They prevent certainty from settling too comfortably. They widen the space in which wonder can breathe. There is also a quiet emotional beauty in seeing these patterns echo across such different scales. From a star flickering irregularly 1,000 light-years away, to a transient flash lasting 1 millisecond, to a ring of galaxies 1 billion light-years wide, the universe expresses its mysteries with a kind of unity. The small and the vast both carry clues. They both invite the same curiosity. When anomalies echo one another, they ask us to listen, not with urgency, but with patience. They remind us that discovery is not about solving puzzles quickly. It is about staying open to the idea that the universe is richer, stranger, and more intricate than we expected. And perhaps the greatest echo of all is this: whenever we think we have reached the edges of understanding, the universe gently nudges the boundary a little farther away. When we look up at the night sky, it is easy to assume that we're observing a finished work, a polished painting hung in the deep, dark gallery of the cosmos. The stars appear steady. The constellations have not changed in thousands of years. Even the faint band of the Milky Way draped across the sky feels timeless. But every mystery we've explored in this long journey, every strange star, every quiet void, every echo of ancient light, reminds us that the universe is not a completed artwork. It is still unfolding, and we, in our brief moment of awareness, are only beginning to see what it contains. This final session is not about explanations or theories. It is about perspective, our place in the cosmos, our relationship to uncertainty, and the quiet hope carried in the mysteries we have yet to solve. There is a gentle truth running beneath all of astronomy. Humans are pattern-seeking beings. We build stories from shadows, connect stars into shapes, and draw meaning from faint glimmers. It is part of what allows us to understand the world, but in a universe as vast as this one, our desire for tidy answers often meets the soft resistance of complexity. Things do not always arrange themselves neatly. Some observations defy categories. Some signals whisper only once. Some curves stretch too far. Some voids grow too wide. At first, this can feel unsettling. We like certainty. We like closure. We like the sense that everything fits. But science, at its most mature, asks us to sit comfortably with not knowing, to hold curiosity in one hand and humility in the other. The wow signal may never repeat. Tabby's star may keep dimming in ways we cannot yet decode. The giant arc may stand as a curve without a sculptor, and the cold spot may remain a quiet bruise on the universe's earliest light. But these uncertainties are not failures of understanding. They're invitations, gentle reminders that discovery is not a single moment, but a lifelong posture of attention. The ability to live with unanswered questions is one of the most powerful gifts of scientific thinking. It keeps the mind supple, it prevents dogma, and it leaves room for wonder, the kind of wonder that does not demand immediate resolution, but instead lingers like twilight at the edge of the evening, soft and open-ended. There is also something profoundly humbling in remembering where we stand. Our entire planet is a small world circling an ordinary star on one arm of a galaxy that contains hundreds of billions of stars of its own. And our galaxy is only one among trillions. Yet somehow, from this tiny place, creatures made of stardust have learned to measure ripples in the universe's first light, trace arcs billions of light years long, and detect flashes lasting less than 1,000th of a second. We have taken the faintest hints, tiny dimmings, brief bursts, delicate temperature shifts, and turn them into knowledge. Humans often speak about how small we are in the cosmos, but it is equally true that we are astonishingly fortunate. Fortunate to exist at a time when the universe is still revealing its secrets. Fortunate to have instruments capable of listening to whispers from far beyond our galaxy. Fortunate to be able to ask questions whose answers may unfold long after we're gone. This sense of continuity, the knowledge that our questions outlive us, is part of what makes astronomy so deeply human. Every new discovery builds upon centuries of wondering. Ancient stargazers traced mythic creatures in the sky. Today we trace invisible structures across unimaginable distances. Ancient philosophers imagined perfect spheres. Today we find imperfect arcs and messy webs of galaxies. But the impulse behind both is the same, a yearning to understand our place in something larger. When we encounter mysteries that refuse to yield their answers quickly, they invite us into a slower rhythm. They remind us that patience is not a burden but a virtue, that some truths take time, that discovery is a conversation across generations, with each new instrument and each new mind adding a quiet sentence to the ongoing exchange. And as our tools improve, new radio arrays scanning the entire sky every night, new optical surveys mapping billions of galaxies, new satellites measuring cosmic light with breathtaking precision, we can expect the universe to reveal even more anomalies, more rings, more voids, more unexpected visitors, more signals that flicker only once. These will not signal disorder, they will signal richness. They will show that the cosmos is not shrinking under our gaze but expanding, revealing new dimensions, new structures, new patterns beyond the horizon of our current understanding. In this way, the unknown becomes not a shadow to fear, but a landscape to explore, a frontier of gentle possibility. As we come to the end of this journey, imagine for a moment that you're floating just outside the Milky Way, looking back at the thin silver river of stars curving through space. From that vantage, our home appears quiet, serene, fragile, and beyond it lies a universe filled with questions that shimmer softly, waiting. It is here, between curiosity and humility, that wonder lives. The universe is vast, older than memory, deeper than imagination. Yet it allows us to see it, to listen to its echoes, to measure its whispers. It invites us to participate in the project of discovery. And in doing so, it offers a simple, comforting message. We do not need all the answers yet. The mysteries are part of the beauty. They are the twilight at the edge of knowledge. They are the gentle promise that tomorrow will bring something new to learn. And as long as mysteries remain, so too does our reason to look upward,